Hi, in this lecture, we will start talking about the finite element method. So we're going to talk about the Galerkian method, also known as the weighted residual method, where the goal is to take a PDE that we are supposed to solve, which is what we call the strong form, and convert it into a weak form that's basically easier to work with and solve the weak form. So we're going to explain this through with the Laplace equation in 2D, or also known as the diffusion equation. So if you consider the Laplacian equation, the strong form written as such, so here really we also have a source term, so you can think of this as a Poisson equation. So we have partial x of k times partial u x. U is a scalar that we're trying to solve, and we also have the same term in the y dimension. And f is a source term, which is a function of x and y. So you can think of this equation as a heat conduction equation. If you take K to be your thermal conductivity, U your temperature, and F a heat source. Or you can think of this also as mass diffusion. If K is your mass diffusivity and U is a concentration field and F is a mass source. So if your material is homogeneous, meaning that your constant K, either thermal conductivity or diffusivity are constant in space, you can take it out of the equation. So your equation becomes in this second derivative form. Now, this equation in the most general case can come with two types of boundary condition. The first is what we call the Newman boundary condition, also known as the natural boundary condition. So this could be imposed on parts of the boundary. So in this case, gamma q is the part of the boundary that comes with a Newman boundary condition, and this is defined as a flux. So the flux of the quantity that you're trying to solve is given by some q bar value, which is known. So in this case, our transport problem is a pure diffusive transport equation. So our Newman boundary condition or our flux boundary condition is just minus k partial u partial n, like a diffusive flux. And then on other portion of the boundary, gamma u, we are given the Dirichlet boundary condition, also known as the essential boundary condition, which essentially means that the value of the solution is exactly known at that location. And also, we should know the domain, of course, the geometry to solve this problem. And the geometry, the surface, the boundary comes with a unit normal vector n, which has n1 and n2 components in a 2D problem. So the problem, the strong form of this problem is that we are given K, the material property, F, the source term, and the boundary conditions, and we want to solve U as a function of X and Y. So the idea behind the weak form is that what we're going to do is that we're not going to be attempting to directly solve this equation, but rather what we're going to do is that we're going to multiply both sides of the equation by W, which is a weight or test function. Okay, so weight the equation by W and then integrate the equation over some domain of interest omega. So in this line that you see here, all I've done is that I've multiplied my governing equation by this W, which is my test function or weight function, and I integrate both sides by omega. So now that I've converted myself from a PDE form into an integral equation form, I can use the concept of integration by parts, which I talked about in the last lecture. And the goal is that I would like to reduce the order of derivatives in my equation. So here I'm dealing with the Laplacian operator. I have second derivatives. And we all know that numerical calculation with higher order derivatives or just in types of numerical processing is more difficult and requires more higher order approximations. So what we're going to do is that we're going to do integration by parts on this second derivative term to reduce the order of the derivatives to first derivative. Okay, so this is how we do it. Here we have this partial x term. I'm going to take this partial derivative and give it to W. So that's what I talked about last time. This is how we do integration by parts. Take the derivative, give it to the other term. So in this case, you are left, this is what you're left with, K partial W partial X, partial U partial X, and then the sign changes and becomes negative, okay? So when you take the derivative, you and give it to the other term, you also have to worry about the boundary term. So the way you do the boundary term is that you keep the sign the same, you take away the derivative since partial x is gone, and instead of that, you have the normal vector. Okay, so in this case, since I'm not doing it in vector form, I'm doing just partial x or partial y, I have just the n1 component, the x component of the normal vector, since I'm doing partial x. This will be my boundary term. Exactly the same, we will deal with the y derivative. So take the derivative here, give it to the other terms w, and just write down that whatever is left with a negative sign, and also deal with the boundary term. The right-hand side will leave as is without any change. Now, if I group the two boundary terms together and factor kw, I'm going to see that this term here looks a lot like a dot product, right? The x components multiplied by each other plus the y components multiplied by each other. And indeed, this is nothing but gradient of u, which is this vector that you see here, dotted with the normal vector n that we defined up here. So this term that appears in my integral term is grad u dot n, or partial u partial n. Okay, and this is integration over the boundary. I have divided my boundary into two parts. I have the Newman part of the boundary, and I have the Dirichlet portion of the boundary. So on the Newman portion of the boundary, I exactly know what partial u partial n is. It's equal to minus q bar over k. So this is from the boundary condition. So if you look back at the Newman boundary condition, I can replace this partial u partial n here with the knowledge of the Newman boundary condition that I have, and I can only do that on gamma q, which is the Newman portion of my boundary. And q bar is a known value. But then I also have this term, so kw partial u partial n, integrated over the Dirichlet portion of my boundary. And interestingly, I do not need to worry about this term because of this very, very important fact that w, the weight or test functions, are always 0 on the Dirichlet portions of the boundary. So whenever you have a Dirichlet boundary condition, you do not have any variations or no weight function. Weight function has to be 0. So now, why is that? To explain this clearly, we need concepts from, or the best way to explain this is through calculus of variation. So I'm not going to talk about calculus of variation in detail, but you can spend an entire course on that. But I strongly encourage those of you who are interested in learning more about the mathematics of finite element to study calculus of variation a little bit, because if you do, first of all, calculus of variation is one of the most beautiful topics in mathematics, and also you will see a lot of concepts in finite element will start to make sense better when you know calculus of variation. And this is one of those concepts. So I'll just briefly mention it here. So we can think about these weight functions, these W's, or these test functions that we multiply our equation with, as some sort of allowable variation. Okay, so that's what we show in calculus of variation with delta u. Okay, so this is it could be interpreted as some sort of variation of u. Okay, and this means that really what I'm doing in finite element is that I have a space of all allowable functions. So these are functions with certain regularity, certain smoothness, certain mathematical properties. It's a huge space of all possible functions within those properties. And what I'm really interested in finite element is to find the optimal solution or the optimal function within that space of all possible functions that best satisfies my equation. And the way I do that, or the way you can look at it from a calculus of variations point of view, is that you're really looking at variations of u. You're taking the solution u and you're varying it within the allowable space. Inside the space that you're allowed to seek the solution, you vary u to optimize and find the solution. So that is how you can think about, or one way you can think about these tests or weight functions w, as these are allowable variations within a space of functions where we're seeking a solution. Now, if you think about it this way, then what you'll see is that on a dirichlet boundary, so on the portions of the boundary where I exactly know my solution, the space of allowable functions is essentially fixed because I know my solution exactly on that portion. Okay, on this boundary gamma u, I exactly know my solution. So I am not allowed to vary my function u in that portion of the domain anymore, which means that w has to be equal to 0 on the Dirichlet portion of the boundary because I'm not allowed to vary. I don't need to vary to seek the optimal solution. I already know the solution. And in other words, the solution is fixed. Okay. You can also think about W as virtual displacements. And since if you remember from your dynamics or courses, you can think of it as virtual displacement. And then, on a portion of the boundary where you have a fixed displacement, you do not have the virtual displacement anymore. Okay, so this is why we have this highlighted important condition. Okay, great. Now I can write the final form of my weak form like this. I have my diffusion term, the Laplacian term, which I've now distributed thanks to this weight function W. So I'm only dealing with first derivatives. And on the right-hand side, I have my source term, and then I also have a boundary term. So this is the only term that's integrated over the boundary, and that involves my Newman boundary condition Q bar, and this integral is only on the Newman portion of the boundary. Okay. Now, one thing you can see here is that we'll talk about this later. When we go about discretizing and solving this equation, we enforce the Dirichlet boundary condition exactly. However, as you can see here, the Newman boundary condition Q bar is really not exactly satisfied anymore. It's become what we call weakly satisfied. It's got absorbed into the governing equation, which is something really beautiful. Like, think about it, your Newman boundary condition, your flux boundary condition is now integrated within your governing equation. So just like when you solve your governing equation, you have some sort of approximation, you're not going to be exact. Satisfying your Newman boundary condition is also going to be some sort of approximation. You're not going to be exact. But for Dirichlet boundary condition, you can enforce it exact. Of course, there will be errors for the Dirichlet boundary condition as well, but those are really the errors of solving your linear system of equations, which we'll talk about later. Okay. Now, this is the derivation using the scalar form, but throughout the course, we will not write equations like this. I will be using a vectorial notation from now on. And so now we're going to rederive this equation in vector form. So let's consider this Poisson equation now written in this vector form. So I have divergence of k grad u, where this is what k grad u is. U is a scalar, so grad u, k is also a scalar, grad u is a vector. And divergence of k grad u is exactly what I had in the previous form of the equation, written in terms of x and y. Now, if k is constant, if my material property is uniform in space, I can take it out of this derivative, and then I have divergence of gradient, which we talked about last lecture, is nothing but the Laplacian. So this becomes my governing equation. The conductivity or the diffusivity times the Laplacian of u, my unknown scalar field, is equal to some source term that I know. Now, let's derive the weak form together. Just like the scalar notation, we multiply both sides by w, okay? So, and then integrate over the domain of interest, omega. Now, I have second derivative here acting on my u, and my weight function has no derivative on it. So what I'm going to do is that I'm going to distribute the derivatives more evenly. So in that way, I can reduce the second order derivative to only first order derivative. And this is how I do it. I use integration by parts. So I take this derivative and I give it to the other term. So here you get grad w, and then you have the dot grad u, and then k is also multiplied there. And the sign changes. Whenever I do integration by parts, I also need to do the Newman boundary. So for that one, or the boundary term, and for that one, what I do is that I just take the derivative, take it out of the picture, and replace it with a normal vector. Okay, so just the derivative, the gradient is out, and I replace it with the normal vector. So this is why I get grad u dot n, and then also have k times w there too. And grad u dot n, the dot product of gradient of u with the normal vector on the boundary, is what we can also call partial u partial n, which shows up in the flux definition on the boundary, which we know exactly what it is. This is from our Newman boundary condition. Okay, and this integral, again, is just evaluated over the Newman boundary because the variations, the weights, the test W are 0 on the Dirichlet boundary. Okay, so then this becomes the final form of the equation. I have minus k grad W dot product with grad U, and then integrated over the domain. And then I have the right-hand side, the source terms. I have a source term coming from the Newman boundary condition and a source term coming from the heat source F. And I can show these with this notation. So this term I show as an operator B of W and U. So give me two functions W and U. B of W and U is an operator where you take the gradients of W and U, you do the dot product, you multiply it by K, and you integrate. So that's how I'm defining this operation. And these parentheses open close are the inner products, the L2 inner products that we previously defined. So they're just take the two functions, multiply each other, integrate over the domain. And if the domain is not clear, we can use the subscript here to denote where integration is done over. So in this case, over the Newman boundary. Now, for this term here, notice that U and W are scalars. So W is also a scalar because our unknowns U are scalars. So W is also a scalar that we multiply by the scalar equation. So these gradients are both, when you take the gradients of scalars, the gradients are both vectors. So this term here, grad W dot, the dot is missing here, dot grad U, this is simply the dot product between two vectors that you can write like this. And this is how we saw it in the previous form of the equation up here. Now, this is how we can summarize the big form of the equation. You can write it as such, okay? So U is your unknown function, W is your test function, and you have the boundary, Newman boundary term, and the source term. Now, you might ask is that, well, what if U and W were vectors? Then what would happen to this operation here? Well, if U and W are vectors, which we'll see later, for example, displacement or velocity, the gradient of a vector is a second order tensor. So then when you have this product here between grad W and grad U, it's no longer a dot product like this, but this is like this double dot product where you take two tensors. In this case, grad U is a tensor, second order tensor, grad W is a second order tensor. You multiply them together and you want to get a scalar at the end. So from all these integral equations, you want to get a scalar. So this double dot is a product that takes two tensors and gives you scalars, and it's defined like this. You can think of it as the trace of the first matrix transpose times the second matrix, which when you do this, you get a scalar. Okay.